Okay, so today we're going to learn about the satisfiability problem. We'll look at the overview. Basically, what satisfiability problem is, it's the first NP complete problem that was developed in computer science. It was developed by Stephen Cook in 1971 at University of Toronto with his friend named Levin. So basically, we have a theorem called Cook theorem, which proves the first NP complete problem. And we have a picture of him here if you want to look at him, what the guy looks like. So what is this satisfiability problem? I'll explain you that. So basically we have a Boolean formula which will return true or false, and satisfiability problem says that it will always return true, therefore it's satisfiable. So here's an example. If you look at it, A and B and C, which will always return 1 or true, because when you have A is equal to 1, B is equal to 1, and C equal to true, or 1, which will be always true, so it's satisfiable. Versus if you look at A not and not A, which always return false, because therefore you can't satisfy that because it's always going to be false. So how do we prove that it's NP complete, basically? So step 1 is to show that SAT or SAT is NP. It's the easier part of step 2 of all the steps. So on the step 2, we look at all the problems that are already in NP and how do we convert that to SAT. So basically, in a way, if you want to put it all together, it is the first NP complete problem, and then basically it has its own category now called NP complete. So basically we have the problems called P and NP, and inside of NP there's a thing now called NP complete since 1971. So Hirsch will explain you now how the proof works.
So the proof works in two small steps. In the first step, we basically have to show that SAT is in NP. This step is the easier of the two steps, since we can use some of the basic reducibility techniques that we learned in class to show that SAT is in NP. In this step, you first start off by guessing. Let's say that A is equal to 1, B is equal to 0, and C is equal to 1. Using the Boolean formula in the previous example, we know that if you have A and B and C, this function or this Boolean formula would return a 0 or false. Second part, you run it through the Turing machine, or I guess you work it out and say if the formula returns a true, you accept, else you reject. So in this case you would reject, and then you would try to come up with a new configuration for A or B or C and see if those configurations work for that particular Boolean formula. And you repeat until you find something that is satisfiable or you reject it. So the second question that comes up to you is, why is this NP? Well, when you think about this, you realize that the possibilities of configurations are endless. There are going to be some easy problems that have two variables, such as A and B. They're going to have 4 configurations. But sooner you're going to run into problems with more variables, maybe 10 variables, and they're going to have 1024 different configurations. We can easily see the exponential nature of this problem, and that's why we need a non-deterministic Turing machine to solve this problem in polynomial time. Therefore, we can say that this problem is in NP. In the second step, we intend on giving you a very basic idea of the proof. First thing is that As soon as we prove this is in NP, how do we come up with this new category called NP complete? Well, in order to do that, we have to show that that all the other NP problems in the NP category can be reduced to satisfiability. We have to start off by making some assumptions about the NP problems. The first assumption is that all NP problems have a non-deterministic Turing machine that accepts them. And again, we have to realize that all the Turing machines are going to have multiple stages, and each stages or states are going to have different configurations. Each state can lead to a different state on a given formula or a given input. So again, that shows you the non-deterministic nature of the problem. And again, if the Turing machine accepts it, it's a satisfiable problem, else we don't have it, satisfiability. Here's a better visual of this problem. Over here we have a two-dimensional array of Turing machines. This is the image Cook used to solve his problem. Each of these Turing machines have different configurations, one unique from the other one. And what you do is you decide on some basic transition functions for each of these, or for all of these Turing machines, and then you run through each of these Turing machines and see if this Turing machine accept or reject the input or the Boolean formula. If even one of these Turing machines accept, then we know we have a winning configuration, and therefore the problem is satisfiable. Else, you go through all the Turing machines and you realize that there's none of them that exist that can accept the formula, and then you have unsatisfiability.
So how do we show that something is sad? So basically we will have an explosion of Turing machines at the end of the day. Let's say we have A and B and C again. How do we know this is satisfiable? So basically we'll have a power set. Will be 2 to the 3, so it'll be 8 possible configurations. And all the possibilities basically means we brute force everything until we get the truth value or return true. So for now, when you have 3 variables, we'll have to go to 8 configurations. But now imagine you have 1,000 variables. Then basically the possibilities would be endless, like her said again, and you will waste your whole life solving that. So in a way, that is why it's so difficult to solve NP complete problem. So again, we just have to brute force everything. So how did it change the CS world? So basically, there's a technique called proof by reduction, where you take one NP problem and you try to connect it to SAT problem. And if you can manage to do that, then you have a solution to your problem. And we have a bunch of them. For example, if you go back here, we have a scheduling problem or 3 coloring from the last lecture and so forth. So is that a big deal? Of course it is a big deal because nobody has found a better solution today to solve NP complete problems yet. So basically there is no solution out there that says, yes, we can solve this. Or nobody even tells us that, hey, we can't do this. So we're in a kind of mess right now. So some people say there's a hope. Some people say we don't know if we can solve it or not. So that's a problem. But the good thing about NP complete problem is that it's a category where you have to solve one problem out of thousands, I think, or less. I don't know that part. But if you solve one problem, you will have a solution to all the problems that are in the category of NP complete. Or basically you have a solution to that in a better algorithm for it in an optimal time consumer. Or if you solve one, there's a reward for it. So if you're trying to pay off your loans, basically, you can try to solve one and pay off your loan, and life's good after that. So we have some references we use here. Other than that, that's all we have for this topic. Thank you very much.
Thank you so much.